Hello, welcome to the ADVA presentation in this Edge Compute and Disaggregation session. If you have been at this interesting show already last year, you might have joined our presentation about optical network disaggregation in combination with SDN control. We've done a presentation jointly with Telefonica, and it looked at work and results, introduced some demonstrators, developed within the TIP Telecom Infra project framework. Today the focus is on 5G connectivity networks, and here looking at disaggregation of packet networks, and also looking at timing and synchronization in a disaggregation context. But before diving into technical details, initially let's look at what is driving the need for innovation in mobile networks. On the left-hand side, a diagram from STL, historic data on revenue growth in mobile networks, concluding there's not big hope for mobile network operators to grow revenue by adding simply bandwidth. The mobile users are not willing to pay much more for more bandwidth. And also looking into the future, that's shown on the diagram from Ericsson on the right-hand side, there's not big hope that with this typical communication services in fixed or mobile networks, the growth rate is pretty moderate. But there's hope. There's other market segments, enterprise, a lot of operational processes now require support from IT networks, resulting in a need for connectivity of any site, any device at a site, any sensor at a site, and this creates huge opportunities also for mobile networks, and 5G is especially designed for addressing those. You might have heard of those applications like massive machine type applications or ultra reliable low latency applications. This is addressing will be addressed by 5G, and this is what 5G is built for. So huge opportunities with 5Gs. On the left-hand side, with some figures, much more bandwidth. Obviously, 5G is using not only low band but also mid band and very broad spectral slots in the high band range, and this provides much more bandwidth per radio base station, but also within a much denser cell. But also low latency, high reliability. This is how 5G is designed, impacting obviously also the connectivity network, which needs to scale much faster, much more efficient than presently designed connectivity networks in 5G. It needs to be agile, easy to operate, automated, functionally extensible with virtualization. So a lot of new capabilities. And shown here with this out of balance, this should indicate what you should not end up is with investing more to get all these capabilities than you gain from your network. So you need an architecture for your network which allows you to address all of that without over-investing in the network. And this is what this aggregation approach will provide you with. One more comment on that one. If you look at present development of 5G networks, you see a very inhomogeneous approach. In some regions, for example Asia Pacific, there is some willingness of mobile users to pay more for more bandwidth. So building a 5G network for the mobile user is an attractive approach. While in Europe, this is not that well developed, this interest of the mobile user to pay more for more bandwidth. Here there's a strong focus on enterprise applications. For example, in Germany, already today there is more than 70 licenses for 5G networks, which are with enterprises, production companies, car industry is very engaged in that one, but also transportation like Deutsche Bahn. US, America's mixed picture, fixed wireless access has been taken up pretty early, so massive bandwidth scale. What I want to say with this is there's different use cases of 5G And what you should not do is you should not develop your network for a specific use case, and this is also relevant for a connectivity network, but the connectivity network should be able to future-proof, provide all those capabilities for you in a seamless, evolving approach. And this is, again, what disaggregation will provide you. Before going into the more details of the connectivity network, some architectural considerations which are relevant for the design of the connectivity network. You heard about front haul. Front haul, the approach that the legacy way of building radio base stations with quite complex functionality, the complete creation of the complex radio frequency signal from a user data flow in combination with the processing control protocols has been done in a BBU broadband unit within a radio base station. For scale, for efficiency, front haul is separating this BBU from the radio base station, centralizing it, creating economies of scale, and this already has been applied with 3G and 4G networks at the expense of much higher bandwidth between this more centralized BBU and the more simpler remote radio head. With 5G, this differentiation goes even a step further. There's now the BBU segmented into a radio unit, in a distributed unit, and in a centralized unit, giving the mobile operator much more flexibility on how to design and implement a network. Between those different building blocks, there is well-defined interfaces for the connectivity network, and as you come closer to your radio base station, the bandwidth is steadily increasing. I'll come back to that one. So this is the target architecture for 5G developed by 3GPP. And with the Open RAN Alliance, this has been augmented with virtualization capability using work from ETSI NFV ISG, so making it a 5G architecture which can implement it in a fully virtualized way. The work of Open RAN Alliance focuses on standardized open interfaces in between, so a pre-requirement to disaggregate something, standardized interfaces on a horizontal and on a vertical level. Gaining a lot of interest in the industry. Within 2 years, there's now 26 major mobile network operators supporting Open RAN Alliance, and close to 200 vendors are supporting this architecture. Also, this is virtualized. Those interfaces between those different building units, RU, DU, CU, those are also in the physical world and need to be supported by the connectivity network. Now let's come back to the bandwidth requirements. Here a diagram from the Open RAN Alliance, and this one is looking at bandwidth requirements for one sector of a radio base station in the midband, high band, midband 100 megahertz, high band 400 megahertz, width of the spectral channel, and different MIMO layers. MIMO means a spatial multiplexing, so reusing the same spectral several times by spatial multiplexing, increasing the usable bandwidth, and comparing that for the F1, the interface between the CU and DU, and FX interface, the interface between the radio unit and the distributed unit. And what you see, bandwidth dramatically growing to, at the F1 interface, tens of gigabit per second, on even going into the 100 gigabit per second range at the front haul interface for a high band application. Conclusion, we need a very, very scalable architecture. Disaggregation is the solution to it. Here looking at a packet network device, historically built single vendor integration of such a switch router. A single vendor is doing all the pieces from designing the silicon, integrating the silicon in a network element, doing the operating system for the network element, and developing the complex routing and signaling protocols. Those vendors might not be the leading technology experts in all of those layers, and any additional feature or scaling this requires a sophisticated development and quite some investment. Things are much easier if you separate this network element. If you separate the layer and get the work done by highly specialized experts companies. That's shown on the right-hand side on this slide here. You see those companies, experts for silicon, experts, ODMs for integrating silicon in bare metal switches, experts like us, ADVA, very experienced in operating networks in the operational processes. We are the experts for designing the network operating systems for those open devices. And on top, there are companies very experienced with higher layer routing protocols and signaling protocols. So this is the approach for disaggregation. Scales very well, and it's a very efficient way. What it requires is a close cooperation between all of those companies. And this is the work which is coordinated, supported under the framework of the Telecom Infra project, jointly working with the Open RAN Alliance presented before. And what the Open Infra project did or initiated some years ago is a complete open mobile architecture using technologies like virtualization, like disaggregation, bringing expert companies together and get the different pieces of the overall network developed. It's probably less than 2 years when initial specifications for a disaggregated cell-side gateway has been defined by major mobile network operators, a specification which was picked up by ODMs, by companies like us to develop network operating systems, and under the framework of TIP, a very close cooperation between mobile network operators, hardware design companies, software companies developed, and over those 2 years they developed what is today a general available, highly scalable solution, disaggregated cell-side solution, a packet solution for the mobile backhaul network, which has been already tested and demonstrated field trials in networks using the equipment which is used in the live network, and we are standing now at the next step, field trial in live networks, and then commercial deployment not too far away of this technology. So very fast innovation stimulated by disaggregation and a close cooperation between those technology experts and stakeholders in the project. You might have watched the TIP Summit a week ago, where a lot of further details have been shared about the progress and the efficiency of this cooperation in the different work streams within TIP, and this disaggregated cell-side gateway is one of the pretty successful projects within TIP. Now let's come to a topic which is getting more and more interest: timing and synchronization. Probably hasn't been so much covered over the last years, but we now see an increasing understanding of the relevance of it, and this is nicely proven also from this light reading survey done end of last year, results compiled by Omdia in this nice diagram, putting timing and synchronization as response from mobile network operators asked for what is the critical and important requirements for 5G on top. Okay, I need to admit all those different technologies and requirements are pretty close together, but one thing should be very clear. If you haven't solved the question and the challenge of delivering precise timing to the edge of your mobile network, you are at risk to use the full efficiency of 5G MIMO technologies, so you will not get the full bandwidth, or even cannot offer some of the low latency, high reliability services. Hence a critical feature and deserves really a closer look at. I showed this architecture, radio unit, distributed unit, central unit before in the diagram. One thing I would like to point out here is that also latency requirements and time accuracy requirements are much higher if you come closer to your radio base station. So between the radio unit and the distributed unit, in this segment, the accuracy, the absolute time accuracy needs to be in the range of 100 nanoseconds and better. That's much tighter requirement than in the CUDU part of the network. Conclusion from that is some mobile network operators build a sync architecture which is optimized for precise time only at the edge. They deploy GNSS receivers at those DU sites, which can be quite high in number, hundreds, thousands even in a mobile network, where they source from satellite delivered time through a GNSS receiver to this last hop of the mobile connectivity network connecting the radio base stations. Sensible approach, however, some disadvantages. First, GNSS comes with some vulnerabilities, some risk of interference from other high power radio frequency transmitters, obstruction from other buildings. That's one of the challenges. The other one, if you operate hundreds, thousands of GNSS receivers, all of them need to be monitored. The accuracy of the time signal needs to be monitored, and that's not an easy task to do. Hence, what we believe is a much more efficient way is synchronization from the core of the network. Put a high reliable, high accurate clock at the core of your network and use a very accurate delivery mechanism over your transport network and provide from the core with redundant clocks from 3-4 sites, reliable, highly accurate time and synchronization information, independent from GNSS, as this might be synced to ITU over a satellite, but those atomic clocks, ultra-precise clocks, will hold this time for days, weeks, even months with sufficient accuracy. How to implement that? Easy thing to do if you think about it at day one. When you, for example, roll out a WDM system, all you should do is consider one out-of-band channel should be available, which is bidirectionally operated, bidirectional for eliminating asymmetric delay. That's very, very crucial thing otherwise for synchronization and timing. And have at intermediate points where you access and need access to time information, a more simple device with a boundary clock. Class D is very important, 5 nanosecond accuracy requirement met, and build an overlay net for synchronization, which can be developed as you need higher and tighter synchronization. So it's a disaggregated, not integrated, disaggregated approach for synchronization. Extremely reliable, extremely accurate, future-proof, but you need to think about it at day one. With this, I'm at the end of my short overview on disaggregation. Today, packet networks was the main focus, ultimately looking slightly at timing and synchronization. Hope you found it interesting. If there are some questions, please contact me over Q&A session or visit us at our booth. Show is almost over for today, but tomorrow there will be much more opportunities to meet. Thanks and have a great event. Talk to you. Bye.